Greetings. Today we'll be talking about exponential functions. So an exponential function is basically a function that can be written in the form, so f of x is equal to a times b to the x, or in the form f of x is equal to a times e to the kx. So both of these are very common ways of representing exponential functions. This is for exponential growth and decay, and we'll discuss the difference in a moment. So here a is called the initial value. And the parameter a is the same for both sides. So on the left and on the right, a would be the same. Whenever you can express a function, an exponential function, in one form, you can always change it over to the other. B is called the growth factor. Essentially, B is the number you would multiply your previous balance by every time you increase the time by 1 unit. So if x increases by 1, you multiply the previous output by a factor of b. So if you start out, so let's take a look at this side. So if you start out, f of 0 is equal to a, because b to the 0 is just 1. F of 1 will equal a times b. F of 2 will equal a times b squared. F of 3 will equal a times b cubed. So basically, every time you increment your x value by 1, you're multiplying the previous y value by a factor of b, and that's called the growth factor. And then this version on the right, instead of having b, we have k. So k is called the continuous growth rate. So in our previous lecture, we used r instead of k, but they both serve the same purpose. And then, of course, e is not a parameter, it's a fixed constant. It's called Euler's number, and it's just simply approximately 2.7182818, and so forth. It's that irrational number we talked about in the previous lecture. So whenever you're describing functions that have exponential growth or decay, you can use either of these two forms. Now, the relationship between the two, the connection, is as follows. Well, we have a on both sides, and then we have b to the x versus e to the kx. Now, e to the kx, note, is equal, so just note this from algebra, e to the kx is the same as e to the k to the power x. So recognizing that, we see immediately what the relationship between these two different ways of representing exponential functions, and that is b is equal to e to the k. So whenever you have the continuous growth rate k, you can always find the growth factor. You just take e to the power of the continuous growth rate, and it gives you the growth factor. Conversely, if you're given the growth factor, you can always find the continuous growth rate. However, that involves natural logarithms, so we'll discuss that in more detail in the next section. But basically, k is just equal to the natural log of b. So that's a relationship. So I'll go, if you're not familiar with natural logs, I'll discuss it more in the next module. So we saw this, that basically this growth factor is the amount by which you multiply the previous outputs by to get to the new ones. So let's look at that. Let's look at a graph. Let's say this is x and this is y. So exponential functions typically look like that. So this might be y is equal to e to the x. And then this might be y is equal to e to the 2x, and so forth. So it would be y is equal to e to the 3x. So the larger the continuous growth rate, so this would be increasing k, or increasing growth factor, so increasing b. So you get something like this. So basically, let's look at our two forms again. Whenever k is greater than 0, we have exponential growth. And whenever k is less than 0, we get exponential decay. Now, if you take e to a positive number, you're going to get a number larger than 1. So this is the same as saying b greater than 1. So when b is greater than 1, you get exponential growth. And then if b is less than 1 and greater than 0, you get exponential decay. So this side makes a lot of sense because, for example, if I have a value of b 1.01, you're growing, right? You multiplying the previous output by a number larger than 1, so it's growing. Whereas if I had b is equal to 0.99, the function would be decreasing, right? Because I'm multiplying by the previous value, the previous output, by a number less than 1. So b will be greater than 1 exactly when k is greater than 0. So those are the two conditions, equivalent conditions for exponential growth. Similarly, b will be less than 1 but greater than 0 exactly when k is negative, and those are the conditions for exponential decay. So there are two other terms that come in handy. One's called the half-life. So this is for the case of exponential decay. So the half-life is simply the amount of time it takes for the initial amount to be halved. Right, so if you start off with 100 grams of uranium and 10 days later you have 50 grams left, the half-life would be 10 days. That's not exactly the half-life of uranium, but it gives you the idea. And then there's a similar concept for exponential growth, and that's called the doubling time. So half-life and doubling time. This is for exponential growth. And like the name suggests, it's simply the amount of time it takes for a population to double.